Good morning, everyone, to day 3 of Vulkanized 2024. I'm hoping everyone has enjoyed themselves so far. We have a bit of a long day, but I'm excited for pretty much all the talks that we have going today. So I hope that everyone enjoys themselves and they bring their questions. To start today, we have Faith Ekstrand from Calabria and Iago Toral from Igalia. And they're going to talk about, well, a bunch of drivers. Please, Faith and Iago, take it away.
Thank you. So welcome to 8 years of Open Drivers. The idea for this presentation is we want to give you an overview of a bit of the history of Vulkan in Mesa, the different implementations that we have and what's the current state of them. We also want to sort of give you some insight into some of the developer tools that we have. And maybe you will find some of these potentially useful for you. And we want to wrap up the presentation discussing a little bit why we think that open drivers are important for the Vulkan ecosystem and how they can also make they can enable you to do maybe a better job on your applications. So let's start by introducing ourselves. My name is Iago Toral. I work as a graphics engineer at Igalia. I've been involved with Mesa for about 10 years now. I started working on the Intel driver stack, and nowadays I'm involved with the Raspberry Pi stack, where I'm focusing mostly on the Vulkan part. Faith.
So I am Faith Ekstrand. I have been around Vulkan for quite a while. I wasn't there quite at the beginning, but I was definitely there for about 9 months before the launch. And at the time, I was at Intel, where I led the Vulkan driver efforts for about 6 years. These days, I am at Calabria, which is an open source software consultancy, where my role is basically Linux graphics architect at large. I'm supposed to be doing whatever needs to be done all over the Linux graphics stack to make things better. Within the Mesa project, I am what we call a maintainer in the open source world. And my primary areas of focus are the Mirror Shader compiler, which is our optimizing compiler core, as well as the SPOV frontend for it, the common Vulkan runtime code that we have that all the drivers share amongst each other, as well as I've spent the last almost 2 years now working on a new open source driver for NVIDIA hardware. We're not going to talk a lot about that, but it will come up a couple of times. So a little bit about the history of Vulkan and Mesa. So it started in 2015, which if you know your dates, that's before 1.0 launched. It was started by me and 2 other engineers at Intel, and we built a Mesa driver for Intel, which we were able to release as a conformant implementation alongside the Vulkan 1.0 spec. And that's something I'm personally very proud of, given that only half the industry was able to do it, and we were able to do it with open drivers. It took about 2 months to land that in Mesa because we had to do a bunch of refactoring of the Intel driver stack, and we couldn't really talk about the refactoring we needed to do before Vulkan was officially announced because of NDAs, so we had to just kind of chew all of that up and do it later, but we did get it merged in about 2 months. The next one was the RADV driver, which that's the most likely one you've heard of because it's what powers the Steam Deck and a lot of Linux gaming. That one came about in a little bit later that year, in October. When we first landed, it wasn't conformant, but they had some games running, and it did get conformant. We have the date somewhere. Since then, we've gotten drivers for basically every major hardware vendor. We have Qualcomm, ARM, Broadcom, Imagination, and recently NVIDIA. Not all of those drivers are necessarily conformant to latest versions of the spec, but they do exist and they're shipping. We also have LavaPipe, which is a CPU rasterizer that is built on the same rasterization core as LVM pipe, which is the driver that is shipped for whenever somebody doesn't have hardware acceleration, or if you don't, if your kernel is too old and you need a desktop anyway so you can run the installers, that's running on an LVM pipe. And so we have LavaPipe, which is the Vulkan version of that. One of the other things that we've built over the last 6 or 8 years has been a common runtime. So when we built the original Intel driver, we had just sort of finished getting the node compiler core in place. And we had to write a Spurvy front end for it. We had to do some Windows system stuff. All of that stuff was already pretty common in terms of its shape. And so that got picked up and adopted by RadV fairly quickly, although the Windows system implementation was originally just a copy and paste and not actually code sharing, but we fixed that. Since then, we've kind of started pulling common pieces out as we've seen the patterns emerge. We didn't try to build common first because, well, first of all, when Vulkan 1.0 started, the idea was it's so thin that there's all the common code is just GL slang and it's in the applications, right? That's not actually true, but that was the idea. And so we also didn't have a lot of experience with it. Like with OpenGL, we had decades of experience working with the API, so we kind of knew what shape things needed to take. But with Vulkan, we didn't yet. And so initially, RadV just copy and pasted the Intel driver and went off and replaced all the Intel bits with AMD bits. But we've since kind of pulled stuff into common code. And we've also built some other pieces that have been helpful for drivers, like when we were doing timeline semaphores, we got that wrong in the Intel drivers, and we got it wrong in RadV, and I think we got it wrong at least one other place before I finally decided to get it right and put it someplace where everybody was using it. Because timeline semaphores on Linux are actually really dang tricky, but we did get them working. We also have like some stuff that implements render passes in terms of dynamic rendering. So the desktop class drivers don't implement render passes anymore. They just implement dynamic rendering, and the common code implements render passes on top of that. I just did some work to do a similar thing with pipelines and shader object. So hopefully in the next couple of weeks, I will be landing shader object support in NVK, at which point it will not contain any pipeline code. And the common stuff just turns pipelines into shader objects, and off you go. And we continue to build out this core. It's a work in progress as stuff emerges that is useful to do that. There isn't really a roadmap or a plan for that. It's just as the API evolves, we keep on having the new way and then the old way. And so we're trying to sort of make it so the drivers are always on the edge and we can backfill for them. Here's a quick timeline of all of the different drivers. There's actually a couple that I'm missing. In Mesa, this is all the hardware drivers and sort of where they are at in terms of conformance. Intel, again, hits all of the beats exactly at the spec releases. RadV is not very far behind. That's the AMD line below it. And then we have a bunch of other drivers. The one bit of information that's kind of missing here is right now it looks like NVK is at Vulkan 1.1, but I actually submitted 1.3 conformance last week. So that one will be a nice solid red line soon. So yeah, that's a quick overview. And we also, if you want to look at sort of in more detail, extension by extension, there's this website called mesamatrix.net. And this has for both OpenGL and Vulkan, basically every feature that exists in this giant matrix, and you can see what drivers implement what things. And that's been useful for us as developers, especially when like I'm bringing up a new driver and I want to see how does this compare against drivers that already exist? What work do I have yet to do? This gives me a quick overview. It can also be useful for developers if they're trying to target Linux to know what can I actually assume is there. There's gpuinfo.org, which is another fantastic resource that has more detailed information because it's got every single Vulkan property and anything you want to know. But if you're just looking at kind of a 1,000-foot view of what features are where, we have this. So yeah, I'm going to hand it back to Iago, who's going to talk to us a little bit about layered drivers.
Yeah, so other than the Vulkan implementations that Faith just showed, there is a bunch of layer drivers that we also have. So one is Venus. So Venus is targeting virtualized environments. So the idea here is to provide a Vulkan driver that can be used by the guest OS by leveraging the native implementation on the host. This was merged in April 2021, and it's, I believe, supporting Vulkan 1.3. Then we have Tosin, which is Vulkan over DX12. The idea for this is to support Vulkan on Microsoft platforms where there may not be a native Vulkan implementation available. And this was merged in March 2022, and I believe it supports up to Vulkan 1.2. And then we have Sync, which is OpenGL over Vulkan. The idea here is with Vulkan becoming more the standard going forward, there may be situations where vendors may only want to focus on Vulkan alone, but still need a story to support OpenGL and sync with the solution for that. And this was merged in October 2019, so it's been a while. It's been on the repositories for a while already. And this supports up to OpenGL 4.6. Okay, so I mentioned in the beginning that there's a bunch of developer tools that we have in the ecosystem. These were intended for driver developers mostly, but some of these can actually be useful for application developers as well. So I just go quickly through some of the stuff that we have, and you will be able to decide by yourselves which is useful for you or not. So one of them is, well, let's start with some environment variables. So one of them is Mesa VK Trace. So this was initially developed for Raspberry, and the idea is to you pass a comma-separated list of trace types that you want to dump, and these are for integration with the Radeon tools like the memory visualizer, GPU profiler, ray tracing analyzer, but it's not really exclusive necessarily to the Raspberry drivers. For example, Intel added support very recently for the memory visualizer dumps as well. So once you have set up this environment variable, you then have another variable that you can use to specify when you want to capture, and that's Mesa VK trace frame. Here you just pass an index with a frame index that you want to capture, and it will just capture that. Or if you want to have some kind of more dynamic control over the exact moment where you want to capture the trace, you can use Mesa VK trace trigger, and here you pass a path to a file, and when that file is created, it will automatically trigger the capture. We also have Mesa VK WSI% mode, and this is useful to override the presentation mode in the swap chain, and to kind of give you an idea how different percent modes work and what they give you. We also have headless swap chain, but it's not probably very useful for application developers, more for driver developers, I guess. So this basically enforces a headless surface, so kind of to get the presentation stuff out of the way. We have Mesa VK abort on device loss. This might be useful for application developers. The idea here is the moment that you get the device loss error, everything that comes after that is undefined, so you can get all kinds of artifacts and weird error messages, and you may lose track of where all that started. So with this, you will get the implementation to abort immediately, and you can say, oh, okay, so this is the place where things started to go wrong, and you don't get distracted by all the trash that comes after that. We also have Mesa VK enable submit thread. So with this, some implementations in Mesa may already be using a submission thread for the queue submissions, but with this, you enforce all the implementations to do that. This may or may not modify the performance behavior of your applications. So you just may want to give this a try and see if it makes a difference for you. But the really meaty stuff, I think, is in the per driver variables. So these are each driver in Mesa typically has a debug variable that you can specify with a number of parameters that control various aspects of how that driver is going to work. And this range from things like getting shader assembly dumps to enabling or disabling certain optimizations or behaviors of the implementation and things like that. So you have to go into each driver to see what's available here. Some of them accept help as value, and they will just dump the list of options that are supported and a brief description for each one. But this can be really useful to really go down into a specific implementation and see what you can do with it. So other than environment variables, we also have a couple of layers that may be useful. One is Mesa device select. What this allows is basically to force selection of a specific implementation in systems where there's more than one available. So the idea here is this, when the layer is active, it will check this Mesa VK device select environment variable. If you set it to list, it will just dump the list of implementations that are available. And you see here there is a hexadecimal ID for each one, and then you can use that to choose the one that you want. You pass it to the same environment variable, and it will force selection of that. particular implementation. The other one that may be useful is the Mesa overlay layer. So the idea for this is, I'm not sure if it's very clear on the image, but on the top left corner, there is an overlay in render where it's showing a few things. I think it's the frame rate, presentation times, and this also is integrated with pipeline statistics. So basically what it does is it reads this VK layer Mesa overlay config environment variable with a list of the things that you want to watch over time. I will just render them as an overlay there. And this is very convenient because it doesn't require any instrumentation on the application side. It's all implemented in a layer. So if you have the layer and you use the environment variable, it will just pop up. It will just work. Okay, so now let's talk a little bit about why we think that open drivers are important to the ecosystem. So let's start with the easy one with this Linux OS integration. So if you already, if you have Linux, obviously there is a tight integration of Mesa. All the Linux distros and BSD, like they all package Mesa in some way. You don't have to, or it all just works. Then there is a lot to be said about application debugging. So there's nothing that we are hiding from you here on closed systems. The driver and the hardware are both a black box. On open systems, you have more options. So all the developer tools I was mentioning before, they are available to you. You can watch command buffer streams. You can dump shader assembly. And also, most drivers in Mesa are going to support things like pipeline executable properties, which is then integrated with RenderDoc. If you haven't seen how that works, it looks a bit like this. This is a capture from RenderDoc with the Intel driver. And you can see here the shader assembly dump for I think it's a fragment shader. And depending on the driver, there's this the amount of detail that you can get here can be very significant. You can see from the initial SPRV different optimization passes that go into producing this assembly, so you can really get a very in-depth view of what code you're producing and how you get there. The other thing is, obviously, you have access to the source code. You can look into how things actually work. I think this is particularly interesting from two perspectives. You may or may not be aware that the implementation has multiple paths for specific things, and which of these paths your application is hitting, for example. So here, if you have, just by reading the source code, you can actually see this. And you can even compile Mesa with debug symbols, set a breakpoint somewhere, see what your application is actually hitting, and check what are the conditions for it to check to hit a different path, for example, and use that to optimize your application or to understand better how the hardware is really operating. On the other hand, if you are having issues like bugs or something like that that you suspect is on the implementation, you can actually go into there and try to figure out what's going on yourself, which may be tricky if you are not familiar with the driver space. But that is another area where I think open development platforms are very useful, because it also means that you probably have an easier time getting in contact with developers. I think that's what phase you want to come in.
Yeah, so one of the really cool things about open source development is that everything that we're doing, for the most part, is as public as we can make it. I have to give a little bit of a caveat there, because we do work on pre-release extensions, and obviously we can't do that completely in the public, but we do it public within the Khronos NDA. So if you are at a university or a company that it has Khronos access, everything we're doing pre-release you can also see. But one of the advantages of this is that it gives a lot better access to developers. So we have an issue tracker at freedesktop.org/mesa/issues. And the developers responded directly. You're not dumping your issue into some black hole of NVIDIA's help forums. You're actually talking to the people who actually write the code. And we also have publicly accessible IRC channels, and some of us hang out on some Discord servers where you can talk to us as well in more of a live environment. So here's an example of this. This was on Mastodon just a week ago. This guy had an issue with the Mesa shader compiler where we were invalidly not doing copy propagation in a situation where we should have, or doing it when we shouldn't, or something with copy propagation was screwed up. And it affected his particular shader in a specific way, and it caused a bug. And he filed it, and within a couple of days, we had figured out the issue, patched it, and it was already in the next Mesa release. And we don't necessarily always guarantee that we're going to fix every bug inside of 24 hours, but it does happen more often than you'd expect. Here's another example, and this one's really cool. So this is an issue that was filed by, name is escaping me suddenly. But one of the researchers who's been doing a bunch of compiler stuff, and I think here in California, where there was an atomic memory operation that was getting optimized away. And this didn't seem right according to the Vulkan memory model to them. And we had this great discussion. We had a back and forth between him and some other people in that same research group and our developers. And eventually we figured out that no, they were actually right. This wasn't supposed to get optimized away. But we can optimize it away in certain scenarios. And so we figured out what the constraints there were, at least well enough to satisfy everybody. I mean, that one gets into deep corners of the memory model. So there are still some open questions about exactly what it means and whether or not we're doing it correctly. But the point of the story is that they were able to get directly involved with our compiler developers. So here we have academics from a research group that are working on trying to work on memory model and modeling GPUs, and we have people in the industry who are actually working on developing drivers and the compiler stacks that run on them that can talk directly to each other in a very open way. There's a couple of other people from Khronos who typically aren't even involved in Mesa that got in on this issue because they're interested in memory and execution model stuff. And this kind of discussion happens fairly frequently. I mean, we don't have memory model bugs fairly frequently, but the ability to have those conversations when there's an issue, it's right there, and we try to get the developers involved in the discussion whenever we can. Obviously, if it's some user that says, I'm running this game from this studio that's never talked to us before, we don't necessarily have contacts at the studio, but we will, if you're running into a problem with your thing and you're pretty sure it's a driver bug, then we'll be talking directly to you. This also enables a lot better cross-company collaboration, where things are getting better within Khronos, I would say, but people are still pretty cagey with each other about things because everybody's, they've got their secret sauce in their driver and they don't want to let anybody else know what it is. We don't keep secrets in Mesa. We don't keep them from our users. We don't keep them from each other. And so when we're developing something like the compiler stack, for instance, we're doing that with fairly complete hardware knowledge. We have people, no one person knows all of the hardware, but we have people who know intimately all of the different hardware that we're targeting, and that combined knowledge can feed into developing the compiler stack. And the same goes for any other common code we have in Mesa, whether it be Vulkan runtime or even our GL state tracker. All of those decisions are fed into by people who have intimate understanding of almost all of the hardware of the industry. And so that allows us to, in my opinion, do a better job of designing those pieces. And for me personally, this has kind of turned into a Khronos superpower because I am able to sit there in the API discussions with more knowledge of what's happening in the industry than a lot of other people within the group do. Most people have I'm from AMD and I know how AMD's hardware works. So I'm from Qualcomm and I know how Qualcomm's hardware works. And those of us who are in the open source world, we know how our specific hardware works, but then we also spend enough time talking to each other that we kind of peripherally know how a few other hardwares work. And it really enables a lot better collaboration and a lot better design of APIs and specifications. Most of us are also Khronos members. So we're all doing all of this public stuff. And there are some people who are just people out in the community or at some random company that has nothing to do with graphics, but most of the people who work on Mesa as their day job are at some company that is a Khronos member. And so everything that feeds into our development, even though it ultimately ends up as source code in a public repo, is fed by the knowledge of what's happening within Khronos and within the view that we can get of the rest of the industry by being in that group. If you are interested in checking out what we've been doing or you want to help out, the code lives on the free desktop GitLab instance. It's kind of like GitHub, only better. People can debate me on that, but I like it better. And we also have a website, mesa3d.org, which is mostly documentation. Some of it is in detail code documentation. And some of it is sort of like getting started guides, like here's how you build it and things like that. And you can also come chat with us. We are on the DRI Devel channel on the OFTC IRC server. Again, we also hang out in some Discords, but none of those are official. That's the place where you can guarantee to find people. And yeah, that's it. Do we have any questions? I already have one hand way up in the air.
Hi, thank you. I'm fairly new to Vulkan, so forgive me. But so last night there was discussion about a software implementation for Vulkan that was reliable. I realize maybe reference implementation isn't the right word for that, but there was a concern that, well, if there's only like 2 developers, say on a project like SwiftShade or something, and they go and they lose funding from Google or whatever, that there's no confidence and backing behind that. But Mesa's been around a long time, has lots of industry support. I was confused why like Lava Pipe wasn't discussed as like not necessarily a reference implementation, but an implementation that developers can rely on for like headless. That was one of my questions. And then the second one is, if I can interject a second, we have a CI system that has, for a variety of reasons, VMware. And we have Windows platforms that can't even run Vulkan on there. And we would love to have a software implementation. And is it possible to get Lava Pipe? What's
Absolutely. Lava Pipe builds and runs on Windows. And I can't speak to why some people are going with SwiftShader instead of Lava Pipe. That's a whole political disaster that I'm not going to touch. But it does run on Windows. And because of the way that Vulkan loading works, it doesn't even need to be like installed as an official driver like the other drivers do. Like with OpenGL, there's this whole thing where the way that it's loaded, it kind of has to be a driver, and there has to be Windows system integration, and it's a whole mess. With Vulkan, if you okay with just running headless, then yeah, you can just build it on Windows and point the loader at the .dll, and off you go.
Yeah. So to follow up on the stability on why that's a great idea to use Lava Pipe in your CI. In Mesa CI, we're obviously using Lava Pipe in some situations, like as the backend for the CI for Venus, which is a virtualized driver that runs in a VM. But in ChromeOS, and ChromeOS has some pretty strict, pervasive, thorough CI. It's kind of absurd how strict it is. Whenever we are testing on VMs, most of our testing in ChromeOS in the CI is on real hardware, but whenever testing against VMs, we always use Lava Pipe inside of ChromeOS. So that's a guarantee.
And we didn't have it on here, but I'm pretty sure Lava Pipe supports most of 1.3 with lots of bells and whistles. Like I think it even supports ray tracing these days.
It's confirmed to 1.3.
Oh, okay. Yeah. So yeah, it's not like half a driver that somebody kind of wrote, like it is actually a real thing.
I don't want to derail that because I think we're going to go further on that topic, but I wanted to ask about performance regression. It's purely a curiosity question. How do you deal with that? I mean, that's a hard problem with so many different platforms and devices.
Performance regressions, generally in terms of what we're doing upstream as community efforts, there's not a lot of performance tracking at the moment. At least when I was there, Intel was tracking performance regularly. In terms of like, how do we deal with regressions? Performance regressions from common code aren't that common. We have had some. I mean, obviously, somebody can write some compiler optimization for AMD that screws up Intel or vice versa. But it doesn't happen that often. And we deal with it like any other issue. Like if there's, but the difference is, unlike, if you're using an LLVM-based compiler, you pull in, the latest LLVM version and suddenly your performance gets completely screwed up. With Mesa, you're taking it constantly. And so if you're tracking it, you catch it within a couple of days and you go patch it.
Yeah, I think the idea is if someone makes a change that affects your particular implementation, you just open an issue, talk to the people, as Fed said, we kind of talk to each other and we just work it together and figure out the solution. I've done that a bunch of times with different people and it just works.
So is it, just to finalize that, is it fair to say then that each of the teams working on a particular architecture has devices with that architecture and is able to do performance regression? And if there is a system-wide issue, it gets reported up that way?
As that team has resources, I mean, some of the teams are like one guy who's working on a driver for some hardware. But the bigger teams like the RADV team at Valve or the Intel team, they absolutely have infrastructure for doing stuff.
Also real quick, since Chrome OS majorly uses mostly Mesa drivers for their devices, and or CI inside of Google, we do performance regression tracking against the drivers too and work with upstream to fix those regressions. Yeah, so like, I guess what I'm trying to say is it's not just on the hardware vendors do performance regression. Mesa is a community project, and it takes the whole community with everybody that uses Mesa to do that CI for performance regressions.
We have 2 questions left, and then we're going to move on.
Awesome work. Honestly, I didn't know about Lava Pipe until last night. So I'm really glad this is there. I had another question. There was another initiative, OpenSwir, which was supposed to be AVX implementation, uses AVX extensions of similar to LLVM pipe. Does Lava Pipe have a similar thing similar to OpenSwir?
So I'm not sure what exactly they were doing, but yeah, Lava Pipe does take advantage of some of the AVX instructions. I'm getting to the edges of my knowledge here, but it natively runs in a SIMD way, and it does use those features when they're available. I don't know if we haven't necessarily deeply tuned it for AVX2 or AVX 512, but like it will use that as much as LLVM is able to, because it uses LLVM as a JIT under the hood. So if LLVM is able to vectorize, then it will.
Thank you.
I couldn't help but notice your slide on device select features both V3D, which is the Raspberry Pi driver, and a dedicated Intel GPU. What's up with that? Does that work?
That was a simulated environment.
I see.
All right, we're going to call it there. One more round of applause, please.